the last video lecture of Chapter 11. So today we're going to talk about Section 11.5, putting it together. Which method do I use? Once again, I am Dr. Scott Spaniel. I am your instructor for Math 141 Statistics at Morton College. So with Section 11.5, putting it all together, this is really just like the other putting it all together sections, is choosing the correct method. So in this section, there are basically three choices. Either I'm doing a problem with proportions, in which case I'm going to use two prop z-test, or I'm doing a problem with means that are dependent, in which case I'm going to find the differences and then I'm going to do a t-test, or I'm doing means but they're independent, in which case I'm going to use a two-samp t-test. So if you open your your note sheets to page 13, you'll see a number of problems. And so what I'd like you to do is pause the video and go through pages 13, 14, and 15 and see if you can do those problems. And then once you hit play, we'll run through them, and I'll do these 6 problems together, and then that'll be it for this video lecture. Okay. So now that you've had a chance to try these, let's go ahead and run through these together. So the first one says TIMSS is an acronym for the Third International Mathematics and Science Study. Kumon promotes a method of studying mathematics that it claims develops mathematical ability. Do data support this claim? In one particular question on the TIMSS exam, a random sample of 400 non-Kumon students resulted in 33 getting the correct answer. For the same question, a random sample of 400 Kumon students resulted in 130 getting the correct answer. Perform the appropriate tests to substantiate Kumon's claims. Are there confounding factors regarding this claim? Okay. So in this case, we're being given a proportion, right? Because we're given an x and an n. For non-Kumon students, we have x is 73 out of 400. For Kumon, x is 130, where n is 400. And so we're dealing with proportions. So our hypotheses would be that the proportion of non-Kumon students would be equal to the proportion for Kumon students. And our alternative hypothesis would be that the proportion for non-Kumon students is less than that for Kumon students, right? And you could flip the order of those, but it would mean the same thing if we flip the inequality as well. So we're dealing with proportions, so that means we're going to use the two prop z-test. And remember, to get to two prop z-test, you can just type in these capitals, so T, P, Z, T. And then we just need x and n for each sample. So x for sample 1 was 73 out of 400. And for sample 2, the Kumon, it was 130 out of 400. And so if we do that, we get a p-value of 0.000002. Okay. So is that less than alpha? You bet it is, right? It's pretty low. They didn't tell us what alpha is, but that's a very low p-value. So we could say we would reject H naught, and we could say there is sufficient evidence to suggest Kumon students perform better on this question. Okay, so that's the idea. Now, problem number 2, number 9 listed here. The age difference in married couples. What is the typical age difference between husband and wife? The following data represent the ages of husbands and wives based on the results from the current population survey. What is the response variable in this survey? Okay, well, the response variable, response variable is age. Okay, Is this sampling method independent or dependent? Well, it's dependent, right? Because we've got them by couple, so we're selected into the groups in groups of two. Use the data to estimate the mean difference in age of a husband and wife using 95% confidence. Okay, so we're going to find the mean difference and we're going to do a confidence interval. Okay, so in this case, what we want to first do is go into our data sheets and get our data for this problem, which is 11.5 problem number 9. So we've got our husbands and wives. And then we want to do the difference between their ages. So we're going to do equals A2 minus B2. And then we want to bring that down so we get all of them. Okay. And so now what we want to do is we want to copy and paste that data into ClassCalc. And we can do a t-interval in order to figure out, using data, in order to approximate the mean difference in age between husbands and wives. So we've got x sub 1, and our confidence level is 95%. Okay, so we've got our estimate. So our estimate goes from negative 0.496 to 5.996. Okay. And so what we could say is the mean difference is basically between 0 years and 6 years, if we round those off. So if we rounded to the nearest year. Okay, so that's the idea behind that one. So another example. Do people tend to spend more money on fast food when they use a credit card? The following data represent a random sample of credit card and cash purchases. So we've got our data, right? The first thing they want us to do is draw box plots of each data set using the same scale. What do the box plots imply about cash versus credit? So that's one way we could compare these. So once again, if we go into the data sheets here, we can go into problem number 10 and we can copy and paste our data from Google Sheets into ClassCalc. And then we want to make some box plots, right? So let's make a box plot for x sub 1. And then also make a box plot for y sub 1. And we can tell it to exclude outliers so we can see if there's any outliers. And so if I zoom in on those, this is one thing we talked about in class a little bit, is these can be hard to see. But if we turn one off and just look at the other one, we can see that the green one is farther to the right. And the green one is x1. So the box plots imply that credit. People spend more money with credit, right? Credit. Spend more money. Okay? But now we can also take that a step further and see if that difference is big enough to say that that's always true. So now it says test whether sample evidence suggests that people spend more money when using a credit card. Use alpha equals 0.01 level of significance. Okay. Note that with these are small sample sizes, that these could be normal. Okay. So what we want to do is we should notice, are these dependent? No, they weren't paired up in any way, right? It's not like somebody went in one time and paid cash and another time paid credit. These are just 10 randomly selected credit and cash card purposes. So that means we're going to want to use, because these are independent, we're going to want to use two SAMP t-test. Okay. And we can write our hypotheses, which are, we want to know if they spend more with credit cards, right? So mu sub credit equals mu sub cash is our null hypothesis. And then we expect credit to be more than cash when we do this for, right, when we compare these. So that would be our alternative hypothesis. So we go in here and we do a two SAMP t-test, which is TSTT, and we can put in our data because we're getting it from data. So x sub 1 is the first data set, y sub 1 is the second data set. and there is our our p-values for us. And we said it would be greater, so that's the middle one. So our p-value is 0.0194. So we can compare that to our alpha, which is 0.05, and it is less than that. So that means we can reject H naught, and we can say there is sufficient evidence to suggest people spend more on fast food when using a credit card. Okay, so let's go ahead and skip. I'm just going to skip part C, although it would be unethical to change the level of significance to match what your data results are, although my data results say that it doesn't really matter in this case, although that might mean that I have a typo in my data set. Okay, so let's keep going. So there's one example so far of each. We've got a 2-SAMP t-test, we've got a dependent one, and we've got a proportions problem. So there's 3 examples. So let's keep going to see a few more. So number 13 says, predicting election outcomes. Researchers conducted an experiment in which 695 individuals were shown black and white photographs of individuals running for Congress. In each instance, the individuals were exposed to the photograph of both the winner and runner-up in a random order for 1 second. The individuals were then asked to decide who they believed was more competent and therefore more likely to receive their vote. Of the 695 individuals exposed to the photos, 469 correctly predicted the race winner. Do the results suggest that a quick 1-second view of a black and white photo represents enough information to judge the winner of an election based on perceived level of confidence of the individual more often than not? Use the alpha equals 0.05 level of significance. Now, this is an interesting question that comes up here because I forgot it was in here, but this is actually a problem, I believe, that goes back to stuff from chapter 10, because what you should notice here is there's actually only one sample and one X and one N, right? We only have these 690 individuals, 95 individuals, and we have that they were successful 469 times. So this actually goes back to chapter 10 and is really important because we need to also be able to represent between things in chapters 10 and 11. When do we use 2 sample things and when are we using 1? So for me, this says, what is it? Do the results suggest that we can pick out the winner of an election more often than not? Well, more often than not would be a majority of the time, which would be 50% of the time. So for me, the null hypothesis is here that P is equal to 50%, 0.5, and H1 is that P is greater than 0.5, and we can use a 1 prop z-test to examine this. Okay, so if we go into our calculator here, let's get rid of all this stuff we were just doing, and we do 1 prop z-test, we can put in our P naught is 0.5, our X is 469, and our N is 695. And we should get a p-value that, since we're doing greater than 0.5, is basically equal to 0, which is indeed less than alpha. And so the results of this do suggest that we can, with a quick 1-second look at 2 candidates, decide who's going to win the election. Okay. So here's an example going back to the last chapter even. Okay. So let's look at a couple more, and then you'll have a bunch of examples, and you can try these problems on your own in the homework. So number 14 says, bribe them with chocolate. In a study published in the Journal of Teaching of Psychology, the article Fudging the Numbers, Distributing Chocolate Influences Student Evaluations of an Undergraduate Course, states that distributing chocolate to students prior to the teacher evaluations increases results. The author randomly divided 3 sections of a course taught by the same instructor into 2 groups. 50 of the students were given chocolate by an individual not associated with the course, and 50 of the students were not given chocolate. The mean score from students who received chocolate was 4.2, while the mean score for the non-chocolate was 3.9. Suppose the sample standard deviation of both chocolate and non-chocolate was 0.8. Does chocolate appear to improve teacher evaluation? So what we have here is 2 samples that were given the mean, and they are independent of each other, right? They're not linked together. So this will be a 2-samp t-test. So H naught and H1. H naught is going to be that the chocolate, the mean for the chocolate equals the mean for the no chocolate. And H1 will be the mean for the chocolate is greater than the mean for the not chocolate. So we think the chocolate improves teacher evaluation, so we would expect the score to go up. So now we can do a 2-samp t-test, TSTT, and we can put in the given information. So the mean for the chocolate group was 4.2 with a standard deviation of 0.8 and a sample size of 50. The mean for the second group was 3.9 with a standard deviation of 0.8 and a sample size of 50. And so what we get for our p-value for greater than is p equals 0.0319, which is less than our alpha, right? So that our p-value 0.0319, which is less than alpha. So we would reject H naught, and we could say there is sufficient evidence to suggest that chocolate improves teacher evaluations. Giving students chocolate before they evaluate you improves teacher evaluation. So I'm going to have to give that a try. Okay, and then the last one here that we're going to go through together is there a difference in the attitude towards extramarital affairs in the United States versus Canada? Pew Research surveyed a random sample of adults from 8 countries and asked, do you personally believe that married people having an affair is morally acceptable? Results of the survey show below. So we've got the number of people surveyed and the number responding that it's morally acceptable in both countries. So the response variable here is either yes or no on that. These are independent samples, right? They're people from the United States and Canada that were randomly selected. What approach should be used to determine whether the attitudes in Canada differ from the United States? Well, these are proportions. So we're going to want to use 2 prop z-test. And so we can conduct that a test. So what we want to know is, do they differ? So H naught could be, does the proportion in Canada equal the proportion from the U.S.? And then H1 would be the proportion from Canada is not equal to the proportion in the U.S. Okay. And then we can go ahead and use this data and our calculator to do that sample. So we're going to do a 2 prop z-test, so TPZT. And we can put in our data. So for group 1 Canada, we had 533 saying it was morally acceptable out of 701. And for the United States, we had 841 out of 1,002. And so for not equal to, we get a p-value of 0.00005 for not equal to. So that is less than alpha. So we can reject H naught, and we can say there is a difference in the attitudes in Canada and the United States on when it comes to extramarital affairs. Okay. So that's it for this section. There's a few more videos, a few more examples to go along with the ones that were in sections 1, 2, and 3 about these 2 sample hypothesis testing and confidence intervals. So I hope this is helpful. As always, if you have any questions, feel free to send me an email or a remind message, and I'll get back to you as soon as possible. Other than that, make sure you're doing all your assignments, and have a good one.